everyone. In this video, you're going to learn how to differentiate parametric equations. So how do we find the derivative with these equations? So at this point, you've learned how to graph parametric equations. So let's say a particle is moving along a parametric curve. Then the equation x equals f of t would describe the horizontal motion of the particle. And the equation y equals g of t would describe the vertical motion of the particle. So, what if we wanted to determine the maximum height of the particle, or maybe when the particle reaches that maximum height? Well, we can use calculus, and that means derivative. So, because remember, if the tangent line is horizontal, that's when a graph has a maximum or minimum, so if we could find the derivative, we could determine when the slope of the tangent line equals 0, and that could tell us when the particle reaches its maximum height. So anyway, there are a lot of reasons why we might need to find the derivative of parametric equations. Okay, so how do we do that? So to find the derivative given parametric equations, so if we're given, parametric equations, x equals f of t, y equals g of t, then to find the slope at a point, okay, which would be the derivative with an instantaneous rate of change, we know slope of the tangent line to be dy over dx. So that would end up equaling, with parametric equations, dy over dt divided by dx over dt, as long as dx over dt does not equal 0. Okay, well, where does that come from? Let me show you. So you guys, we already know that dy over dx is the derivative of y with respect to x, okay? So if we're given, parametric equations, so again, let's say x equals f of t and y equals g of t, then by chain rule, if we were to find the derivative, f prime of t would equal the derivative of x with respect to time. So that would be dx over dt. And if we were to find g prime of t, that would equal dy over dt, the derivative of y with respect to time. Okay, so now notice if we were to divide these two, if we take dy over dt and divide it by dx over dt, and let's say I then multiply by the reciprocal, so this becomes dy over dt times dt over dx, and my dt's cross reduce, and I multiply straight across, I get dy over dx, okay? So basically we know that dy over dx is equal to dy over dt divided by dx over dt, okay? So this is the main rule that you have to remember, okay? So that probably looks more confusing than it is. In order to find the derivative, all you have to do is find dy over dt, find dx over dt, and then divide, okay? So let's look at an example. So if c of t equals t squared plus 1, comma, t cubed minus 4t, then remember, we can write this as two parametric equations. So this is telling us that x equals t squared plus 1, and y equals t cubed minus 4t. So we're just going to find the derivative of each of these with Okay, therefore, dy over dx, which we now know equals dy over dt over dx over dt, you know, would equal 3t squared minus 4 over 2t. Okay, now we want to plug in, and this actually would be t equals 3. Sorry about that, you might want to change that in your notes. So now we're just going to find dy over dx when t equals 3. Okay, so now I'm just plugging in 3 for t into my derivative. And then we'll just work that out, and that works out to 23 over 6. Okay, so this would be the slope of the tangent line that intersects the curve at t equals 3. To find my x and y coordinates when t equals 3, all I have to do is go back here and plug in 3 for t, and then I'll have my point, my x coordinate, and my y coordinate. Okay, so I'm just going to do that up here. X would equal 3 squared plus 1, so that would equal 10, and y would equal 3 cubed minus 4 times 3, and that ends up equaling 15. And so now I can write my equation. I have everything I need. So my equation would be y minus 15 equals my slope times x minus 10. And that would be the equation of the tangent line that intersects the parametric curve when t equals 3. Okay, let's look at part B. Find the point where the tangent line is horizontal. Okay, well remember, if the tangent line is horizontal, that means that the derivative is going to equal 0. So we already know what our derivative is, 3t squared minus 4 over 2t. So we just got to figure out when that equals 0. And I hope that it makes sense that a fraction equals 0 whenever the numerator equals 0. So we can just set the numerator equal to 0 and then solve for t. Okay, and I'm going to square root each side, so I get t equals. Now technically we get t equals positive and negative 2 over the square root of 3, but because we're talking time here, we'll go with the positive square root. Okay, now that's the time when the tangent line is horizontal, but we want to find the points. So we need our x and y coordinates. So again, we're just going to take the t over square root of 3 and plug those back in for x and y. Okay. All right, so if I do that, if I plug in the 2 over square root of 3 squared plus 1, that just ends up working out to 7 over 3. And if I plug it in for y, so now we have 2 over square root of 3 cubed minus 4 times 2 over square root of 3. That ends up working out to 16 over 3 square root of 3. Okay, so the point where the tangent line is horizontal is 7/3, comma 16 over 3 square root of 3. So that's the ordered pair, the x comma y ordered pair of that point where the tangent line is horizontal. Okay, now we can also find higher order derivatives of parametric equations, and I can tell you that most of the time you might be asked to find the first derivative and the second derivative. It's probably not often that you're going to have to find the third derivative, but you have it here in case you ever had to do that. But let's focus on the second derivative. So this is the rule that you end up using to find the second derivative. Basically, the second derivative of y in terms of x, okay, ends up equaling the derivative with respect to time of dy over dx, all divided by dx over dt. Okay, so that's the rule. But again, let me show you where it comes from. Okay, so you guys, let's go back to, we know this is our second derivative of y with respect to x. Okay, and remember that came from finding the derivative of dy over dx. So just putting that derivative operator in front of dy over dx. Okay, now we already know with parametric equations that dy over dx equals dy over dt divided by dx over dt. Okay, that was our first rule. Okay, now with a little manipulating, okay, this is equal to the derivative with respect to time of dy over dt divided by dx over dt times dt over dx. Okay, because notice my, if I were to cross reduce the dt's, okay, I would get back here. All right, so these two are equal. Okay, now, let me get rid of those. Okay, now what we can do, instead of multiplying by the dt over dx, we could just divide. So this becomes the derivative with respect to time of the dy over dt divided by dx over dt, which remember that equals dy over dx, all divided by dx over dt. Because if I took this and I multiplied by the reciprocal of dx over dt, it would get me back here. Okay. All right. So what are we doing exactly? Because I know that can be a little confusing. So all you're going to do is you're going to find the derivative with respect to time of the first derivative, and then just divide it by the derivative of x with respect to time. Okay. So we're going to take our answer that we get for the first derivative. We're going to differentiate it, and then just divide that by dx over dt. Okay, let's look at an example, and you'll see what I mean. Okay, and since we can find the second derivative, we could actually use it to determine concavity. So in this example, we're going to determine the intervals of t on which the curve is concave up or concave down. And our parametric equations are x equals sine of t and y equals cosine of t on the interval 0 to pi. Okay, so first we got to find the first derivative. So I would just jump right in, find dx over dt, derivative of sine is cosine, find dy over dt, derivative of cosine is negative sine. Okay, so then we know dy over dx is going to equal negative sine of t divided by cosine of t, because it's dy dt over dx dt. Okay, now we could use one of our trig identities to simplify this. Sine over cosine equals tangent. So we could just make this negative tangent of t, and that might make life easier when we find the derivative. Okay, so now we just have to find the derivative with respect to time of negative tangent of t. So derivative of tangent, remember, is secant squared. Okay, but then we're going to divide that. So my second derivative is going to equal negative secant squared of t, but then divided by dx over dt. So divided by cosine of t. Okay. Now, as far as, so we have our second derivative. So as far as determining the intervals of concavity, everything is the same as what we would have done prior to parametric equations. We would want to determine our possible inflection points. So remember, the possible inflection points is basically when the second derivative equals 0 or when the second derivative does not exist. Okay, so to find my pips, as I like to call them, possible inflection points, we would have to set the numerator equal to 0 and the denominator. Setting the numerator equal to 0 is when the second derivative equals 0, and setting the denominator equal to 0 is when the second derivative does not exist. Okay, and then we're just going to solve each equation. But here's the thing, you guys. In our first equation, if I get secant of t by itself, I'm going to end up with secant of t equals 0. And you guys, the graph of secant does not cross the x-axis. So this actually is not going to give us a solution. But cosine of t equaling 0, we can solve this equation. So we would use inverse cosine of 0, which equals t, and then we would think to our unit circle. Again, we're focusing on the interval 0 to pi, where, meaning for which angle is cosine equal to 0. Well, that would happen at pi over 2. All right, and we would have to set up our sign chart. Now, we're just going from 0 to pi. Okay, so here's pi over 2. And we're going to pick some test values. So I think I probably would just use pi over 4 and then maybe 3 pi over 4, because those are pretty easy to deal with. And we're going to plug our test values into our second derivative. Now, I would look at it like this. Honestly, you could just think about the 0 to pi over 2 is quadrant 1 on your unit circle. And remember that all the trig functions are positive in quadrant 1. Of course, because we have the negative in front of secant squared, though, we'd end up with a negative over a positive, which would be a negative. And then pi over 2 to pi, that's quadrant 2. So in quadrant 2, secant and cosine are both negative, because secant is the reciprocal of cosine. But because we're going to square the secant, that would end up being positive, but then we're going to multiply it times the negative. So in the long run, we'll end up with a negative over a negative, which will be positive. Okay, so we basically have our answers, finally. So we know that this graph or curve is concave down from 0 to pi over 2 and is concave up from pi over 2 to pi. All right. So again, you guys, just kind of showing you that we can still do a lot of the calculus that we've done prior. We're just now applying it to parametric equations. The only thing really different here is just finding the derivative, I would say. Okay, so we just have a couple of new rules for finding the first derivative, which again is easy because it's just dy over dt divided by dx over dt. And then we have our second derivative, which is where we have to find the derivative with respect to time of dy over dx, which is that first derivative, and then divide by dx over dt. All right, well, you guys, we will stop there and do some practice in class tomorrow. So, as always, thank you for watching, and have a good night.